Good morning.
Okay, good morning. Am I audible?
Yes, sir.
Okay. Okay. So we have started this process, shuffle frog leaping algorithm. And in last class, we have discussed regarding the initialization steps. Then second step is the classifying frogs into Memeplexes. So what is Memeplex? We have already discussed. That is Memeplex, it is the colony where actually these frogs will reside. So how these frogs will be distributed among these colonies, so that we'll understand from this particular step. So a fitness function is used to evaluate the worth of each frog. Okay. So fitness function, we know that is the objective function. So objective function, that is basically your fitness function. So this fitness function will determine whether that frog is worthy or it has to be discarded from the colony. Okay. So for example, let us understand that frog has a disease. Okay. So that frog will not survive. Okay. So what will happen? That will be removed from the colony. Okay. So the worthy frog, that means the frog has the capability to find the food within the search space. So those frogs are the basically worthy frog. Okay. So the fitness function or the objective function will calculate, and from that will determine whether. Okay, just a minute. Slide is not changing. Okay, fine. You cannot see my slide, no?
Yes, sir.
Yes, sir.
Okay, so thank you. Don't write in chat, but you just tell me. I will be happy, no issue. Okay, I think there is a problem. So again, I will share. Now, is it visible?
Yes, sir. Visible.
Okay. So we'll distribute these frogs among based on their fitness function or the objective function. Now the frogs are then sorted based on the values of their fitness function in ascending or descending order in a minimization or maximization problem respectively. So we'll understand this thing. So just a minute, I'll connect my board and then I will go to the board and we'll discuss. Just a minute. Okay. So how we are going to distribute these frogs? So that is very, very important. Okay. So for example, let us say we'll take a function fx equal to x1 square plus x2 square. Now you have, let us say, you have a population, let us say 10 population. 5, 6, 7, 8, 9, 10. And this is the variables you have randomly initialized. So let us say this is 1, 2, then 2, 1, then 3, 4. But x1 and x2 both are lying within 1 to 5, for example. Okay. Then this is 1, 5, 3, 4, 3, 2. Then this is 1, 4. This is 4, 1. Then 5, 2. Then 2, 4, 2, 4. Let us say 2, 4. Okay. And this is 3. 5, 3, 5. Okay. So fx you can calculate. What is the value of fx? This is this square plus this square. So this 1 plus 4, it is 5. This will be again 2 plus 2, 4 is 5. Then this is 9, 16, 25. This will be 26. This will be 9 plus 4, 13, 17. This will be also 17. This will be 25 plus 4, 29. This will be 4 plus 16, 20. Then 25 plus 9, 34. So let us say you are shorting it. So when you are shorting it, so for a minimization problem, if the problem is a minimization problem, so we'll short it in descending to ascending, or it will be ascending order. For minimization problem, we'll arrange them in ascending order or descending order. What is your answer?
Descending order.
For minimization problem. For minimization problem, minimization means you are trying to minimize it. So you need to pick up the minimum value. So that means it should be in ascending order. So we should arrange in a ascending order. So like 5, 5, then which one will come? Then 13 will come. So then 13 will come. Then your 17, these two things will come. Okay. Then your 20 will come. Then next is your 25, then 26, then your 25, 26, then I think it is 34. Okay, 3, 3, 6, 3, 3, 6, then 9, 3, 3, 3, 6, 4, 10. Now there is a one digit is left.
29.
29, correct. So this will be 29. Okay. So this way we'll arrange. So that means corresponding variables will be same. So corresponding the same variables will be mapped. X1 corresponding to this, X1 and X2. Similarly, for the maximization problem, we'll arrange them. So for minimization problem, we'll arrange them in ascending order. For maximization problem, this will be arranged in descending order. 25, 20, 17, then 17, then 13, 5, 5, 3, 3, 6, 4, 10. So this will be descending order. Okay, is it clear?
Yes, sir.
Okay. So the frogs are sorted based on the values of their fitness function in ascending or descending order in a minimization or maximization. Now, let us say we'll understand from the figure that the sorting of the figure frogs according to the values of the fitness function. So if let us say fx is a maximization problem, so we'll see that how it is sorted. So let us say these are the frogs. So what I have shown in the in your just with the help of numerical values, it is shown with the help of some figures. So you can see there are different values of the objective function. This actually width is showing the strength of that particular frogs. That means the whatever objective function it is carrying. Now, when we are sorting means it is a maximization problem. Let us say consider it is a maximization problem. So we'll arrange them in descending order. So that means this one will come first, then this one will come. Okay, like that. You can see that their strength is gradually decreasing. So that means for the maximization problem, the best one will be chosen having the highest value. So that particular frog will be selected first. Then the next one, then next one, like that. Okay. Similarly, for the minimization problem, the frogs which is having the lowest value of the objective function will be picked up first, then the next higher one, then the next higher one, and that will proceed till you reach all the values. Okay. So this way, actually, we are going to sort it. Now, after sorting, the frogs are assigned to Z memplexes with Y frogs in each memplex. What has to be done? So you know that the sorting has been carried out. Now we need to distribute these frogs among different colonies, different memplexes. So in each memplex, there will be some certain number of frogs will be present. Okay. So let us assume there are Z number of colonies are there and Y number of frogs are present in each memplex. So let us understand that thing from the figure, or let us say graphic, means with the help of this description. So let us say you have a different kind of colony. Okay, different colony. Okay, these are the colonies, for example. Okay, there are 5 number of colonies. So Z equal to 5. Okay, and let us say in your total number of frogs, we have considered that is population is, let us say, 10. For example, this is a very example. That means your Y is equal to 10. And total is NP is 10. And each colony you have 2 frogs. So in each colony, we'll distribute these frogs. We are going to distribute these frogs. So how we are going to distribute these frogs? So that is the task of this particular optimization. Okay, we will understand this thing from this particular algorithm. So let us see how to distribute this. So the frog with the best value of the fitness function becomes the first member of the first memplex. So the best one will get everywhere the highest choice. Okay, everywhere we have seen the best one is always taken as the best. So that particular best has the option which is open to everywhere. Okay, so then next the second best frog becomes the first member of the second memplex. So that means the highest one will be given the first choice, then the second highest will be given the next choice, then the third highest will be given the next choice. Like that it will be actually assigned. So if you see the actually whatever we have drawn there, so how will assign? So the best one, so that means this best one, let us say if it is a maximization problem, this particular set, that means this 34 means corresponding to this 3 and 5, this is 34. So this one will be given first choice, then this one 29, then 26. So this particular one is going to, let us say, in the first memplex, it is going to the first, then it is second, this is third, then this is fourth, and then this is fifth. Then again it is rotated, then this one will be going to first, then it is second, this is third, this is fourth, and this is fifth. Similarly, for this case, this will be assigned for if it is a minimization problem. So this one will be given the first, then this will be second, third, like that. Third, then it is fourth, fifth. Then again, this one will be given the first memplex. First, this is second, this is third, this one is fourth, and this one is fifth. So like that, they will be given the preferences. So you see, in this example, I have given, these are the memplexes. This is, let us say, first memplex, this is second, this is third, this is fourth, and this one is fifth. Is it clear how we are going to distribute these frogs among the memplexes?
Yes, sir.
Okay, fine. Okay, so the assignment of sorted frogs continue until the jth sorted frog becomes the first member of the jth memplex. So this way, actually, this will be repeated till you reach the last number of frog. Okay, so that means every frog, they will get some location, their colony they will get, and that colony they will actually reside. Okay, so how we are going to distribute these frogs among these different colonies? That is the task of this sorting process. So in the next step, so let us say sorting is done. So we will understand now how we are, what is the step now. So in the next step, the Z plus 1s ST frog becomes the second member of the first memplex and so on. So I have just explained that how we are going to do this thing. So first memplex frog 1, then frog 2, then we'll go to the Zth memplex. The Z plus 1 frog will be the member of the first memplex. Z plus 2 will be the member of the second memplex, and like that. It is going up to 2 plus 2 into Z. So till that, this process will continue. So whatever actually I have explained to you that how we are going to distribute these blocks. So one by one. So first one will be going to first, then second one will be second, third, then third, fourth, then fifth, then sixth one. If you have a 5 number of memplexes, sixth one will be going to the first one. Then seventh one will be going to the second. Like that, it will continue. So this process will continue. So Y and Z are user-defined parameters of the algorithm, and their values are determined by the user. The user means you. You actually, when you will design, when you will write the code, so you are going to define these parameters. So how many memplexes you are going to take, and each memplex, how many procs are you are going to allocate. So these two things are in your hand. So you are going to allocate this thing from your side when you are writing this code for this shuffle frog leaping algorithm. Consequently, the population size M is equal to the Z into Y. Obviously, the population size means how many frogs are there. So Z into Y means what? What is Y and what is Z? Here I have assumed Z is 5 and Y equal to 2. So how many frogs are there? 5 into 2, that means total population is 10. So NP will be equal to 10. Is it clear? Is it clear?
Yes, sir.
Yes, sir.
Okay, fine. So after the population of next step is the frog leaping. So frog leaping means how these frogs will actually going, it is in the forward direction. So leaping process. So how it is going further, going ahead in the further steps. So after the population of possible solutions of frog is classified into several parallel communities, that is the memplexes. The frogs are influenced by other frog ideas within each memplex, generating a so-called memetic evolution. So when within the colony, see everywhere in human beings also, if let us say in a colony, let us say 5 members are there. Now there is a concept of the society, flats. So those concepts are there. So there are, let us say 10 families are locating. Okay. So what will happen? They will exchange their ideas. Okay, they will exchange their let us say information, their emotions, everything they will share. So those are the basically means. In human beings also, we usually share our emotions, our let us say living style or anything, any kind of our day-to-day activities. So we are going to share. So normally you also used to share with your friends. Okay. Normally in your student life, you are going to share this information with your friends. So similar kind of thing it is observed in the frogs also. In that these animals, they also share this information with their inmates or within the colony, they are basically going to share this information. So basically this information is the basically means. So any information which is shared among their inmates, these are basically means. So these means are basically when they are sharing this information, so the weak frog, the let us say least worthy frog, that is gets influenced by the best one. So what will happen? That the lower category or the having the capability lower, those frogs will try to evolve. They will basically try to upgrade themselves. So everywhere in any where every human beings or the living beings, they will try to upgrade themselves. Any animals also, they are basically searching for their foods. So they are only thinking is how they will get their food. Okay, that is that is normally their practice. So how they are going to improve their performance? Basically from their inmates. They are getting their information from their other colony members. So those colony members, they were providing the information, and based on this information, these frogs are basically trying to improve. And this process is known as the memetic evolution. So like your genetic evolution process and particle swarm technique, this is the memetic technique. So this is the memetic evolution. It is going to happen. Now the memetic evolution improves the quality of the being of an individual and enhances the individual frog's performance towards the goal. So obviously when there is a sharing of information, exchange of information, let us say transmission of any kind of ideas between the colony inmates. So obviously there is a evolution takes place, and the quality of the mean that is of any individual, that is going to gets improved. So the overall performance of the frog gets improved. So finally, every frog will try to improve their performance. So the frogs with better means, better ideas contribute more to the development of the new ideas than the frogs with the poor ideas. So everywhere it is happened, every living beings, every human beings, everywhere, when we are getting some better idea, always we are always, it is in the improving nature. So what will happen? Everywhere we can see that this kind of behavior will be observed, and finally we'll get a better kind of ideas, better kind of performance. So those things it is going to observe. So this ensures that the memetic evolution, that is the spreading of superior ideas, selects with the higher probability the best individuals to continue the search for optimum. So obviously what will happen, we will understand that in the memetic evolution process, with the higher probability, the best individuals will continue to search in the search space. So superior one will again perform better. So those with those better performance, they will actually search within the search space, and finally they will get the better quality of the food. So the frog's purpose is to move toward the optimum by improving their means. So always they are trying to improve their means. Means means the information where actually the foods are located. Foods means every living means they are having their own kind of their food habit. So the frogs, they are having some kind of food habit. So those information you can get in the books or the internet. So we are not going to understand those things here, but we are going to understand these things, that when they are sharing this information, basically they will get with this information, they will try to have the better kind of food. So finally they are going to be going towards the optimum by improving the information of the means. So for this purpose, for each memplex, a subset of the memplex called a sub-memplex is chosen for the transmission of ideas. So everywhere we can see within the society there is some kind of cluster. Let us say within a society, 10 number of flats are there. Among that, let us say flat number 5 and flat number 8, they are having a good relation. So that means they are also forming a sub cluster. Okay, there is a sub-memplex. Similarly, in the frogs also we can see, if let us say number of frogs are present within a colony, they also form a sub kind of memplex. And basically, what is the basic philosophy? The philosophy is, when they will form a sub memplex, so the sharing of information within that short group, a small group, will be better. Okay. So in actuality, the sub memplex has Q is less than Y frogs. So Y is your the total number of frogs which is present in each memplex, and this Q, that this capital Q, it is the number of frogs which is present in the sub memplexes. So obviously that will be lesser than the total number of frogs which is present in each memplex. Is it clear? Any doubt till this point? Any doubt? You can ask. Any doubt? Anyone? Do you have any doubt?
No, sir.
Okay. Whether you are understanding what I am actually asking to you, means we are discussing here, is it clear?
Yes, sir.
Okay. Now let us understand what we have actually just now discussed, the distribution of these frogs among the sub-memplexes. So this is the, let us say, this bigger rectangle. This is the entire population, including the gen memplex. So this is the total kind of population which is actually including all the memplexes. Okay, including the gen number of memplex. Now the memplex of Y frogs. So this is basically the size of each memplex, and where Y number of frogs are there. Now within this memplex there is a sub-memplex. So within this small rectangle, this is basically the sub-memplex, a small colony. Within that colony there is a small colony. Okay, so this sub-memplex of Q frogs. So the Y number of frogs, it is present in the whole colony, big colony. Okay, within each colony there are Y number of frogs, But within the each small colony, there are few number of frogs are present. So this is the basically the representation of the memeplex and the submemplex within the entire population. Now, the choice of frogs to form a submemplex conforms to the strategy that superiorly fit frogs have a higher probability of forming the submemplex. So, we can understand from this the choice of frogs to form a submemplex. It is basically who will actually form this thing, the having the higher probability of forming the submemplex. So the best one will be going to the best location. That is the always this is the basically the strategy. Okay. So here also in the frogs also the best one will be given the higher chance, and that particular frogs will move to the better submemplex. And the frogs of a memplex are ranked according to their fitness function. So within the when we have done this sorting process, so after this exchange of ideas, exchange of information, so what will happen? We are also going to evaluate what is their performance. So based on each memplex, there will be a total number of frogs will be there. So based on their performance, we'll rank them. So ranking will be again, there will be two kinds of ranking. One will be if it is a minimization problem, then ranking will be in the ascending order. If it is a maximization problem, then ranking will be on the descending order. So based on that, we are going to rank it. So the probability with which the Q frogs are selected from a memplex to form a submemplex conforms to the following distribution. So if a particular, so this is a kind of isolation, I will tell you that a group of frogs are there within a memplex, and suddenly they are telling that we'll form a small colony. So we'll form. Everybody will try, but yes, we'll form a small colony. So like that in a country, sometimes there is a group of people, they are basically demanding for a smaller state, a smaller district, something like that. So who will actually lead this thing? Who will be the basically leader of this particular colony? So that is based on something. So see, every concept we are actually mapping with some mathematical function. So actually you will be dealing with a mathematical problem, but every mathematical problem, it has a philosophy. So this philosophy we are discussing, and then we are mapping this philosophy with this mathematical function. So how we are going to basically distribute this thing, that is depending upon their probability distribution function. So this probability distribution function, this is based on this function, that is Pj equal to 2 into y plus 1 minus j divided by y into y plus 1, where j is varying, j is between 1 to y. Okay, so this is actually the ratio you are going to calculate. Now the frogs which is having the higher value of Pj will be given the first priority, that yes, you are allowed to form the colony. Okay, subcolony. You are allowed to form the subcolony. Similarly, the next one and the next one, like that. So again, we will rank them based on their probability distribution, and then the highest one will be given the first chance, then the second highest, third highest, like that will continue. Okay, so basically the frogs which is having the highest probability will be given the chance to form this submemplex. So in which, so what is this Pj? Pj is the probability that the jth frog of a memplex is selected from the submemplex. Okay, that is the probability. So who will be selected? Because everybody will try to that, yes, I will be the leader. But what is the quality based on which we are actually judging? So the Pj is the basically parameter which is quantifying the decision-making process for forming these submemplexes. Now J is the counter of the frogs in the memplex. So that is basically counter. This is a kind of counter that how many frogs are there and something like that. So Y is the total number of frogs in the memplex, so that we know J equal to 1 denote the best frog in the memplex. So that first one, that is the 1. So 1 is always the best. So that is the best frog within the memplex, and J equal to Y denotes the worst frog in the memplex. So this is the way we are going to decide. So it follows from the equation 11.3 that the fittest J equal to 1, first frog or the memplex has a probability equal to 2 by y plus 1 of being selected. So let us understand J equal to 1. So J equal to 1 means this plus 1 and minus 1 will cancel. This will be 2 into y divided by y into y plus 1. Okay, that will be y into y plus 1. And the least frog j equal to y of the Memplex is chosen of the probability. So last one. So last one y. So if j equal to y, so this plus y and minus y will cancel. So this will be, that will be 2 into y square plus y. So that way we are going to basically select. So this is the actually formula which is actually deciding which frog will be selected and which frog will not be given the chance to form the subcolony. So the Q frogs are selected to form a submemplex. So the formation of the submemplex, it is basically now it is depending upon the probability distribution function. So they are ranked with the fittest frog having rank 1 and the worst frog having rank Q according to their fitness value. So next, the worst frog in the submemplex is improved. So obviously, always they will try to improve their performance when they are sharing this information or the means. So the worst frog adopts its mean from the base frog within the submemplex and from the globally based frog. So obviously, the worst frog in each memplex, each submemplex, they will always try to improve their performance from which one? The best one, which is basically present within their submemplex, and the globally based one. That means from the all colonies, the best, there will be a best one. So those information, those means are shared with the worst one. So obviously the worst is given the chance to improve. So when there is a significant improvement is observed, we'll adopt those frogs. If it is not improved, then what will happen? We have to discard it. So the best and worst frog in each submemplex and the best global frog in the entire population of the frog are called the M-best. M-best is basically the best frog within the submemplex. M-worst is the worst frog in the submemplex, and P-best, it is the global best, means from the all colony, the best frog is denoted by P-best. Is it clear which one is M-best, M-worst, and P-best? Any doubt regarding the formation of this subcolony or the submemplexes? Any doubt?
No, sir.
Okay. So the mean of the M-worst is improved as how we are going to improve. So M-worst means the worst frog. Worst frog. See, the theory we have understood. The M-worst will take the information from the colony based. Is the colony based means the colony where within the submemplex where that particular frog is located, and from the entire colony. So this is the basically idea. So you see, this is di, a distance vector. It is equal to random into xm best time minus xm worst time. So the difference between the best one and the worst one, this distance is multiplied with a random number. Then it is improved. How we are updating xi dot dash equal to xm worst plus di. So basically we are calculating. The worst one will be calculating the distance from the best one, and then it will add this particular information with its own information. So whatever, let us say the gap with the colony based within this own colony, so that difference is calculated. This is the difference. This difference is calculated and updation is taken place with its own performance. That is the xm worst. Then x new, that is the new one. This is the actually the new variable which is formed. So new will be equal to x1 dash, x2 dash, and until that point. So all the worst within the entire colony will be basically updated with the help of this thing, this formula. So where di is the leaping step size for the if decision variable of the worst frog. So everywhere this di is the basically distance, the difference, this leaping step size, it is the for the if decision variable of the worst frog in the submemplex, and rand is the random values in the range of 0 to 1. So obviously this random value in everywhere we can understand this value will vary between 0 to 1. And then xn base I, it is the ith decision variable of the base solution in the submemplex, and xm worst I, it is the ith decision variable of the worst solution in the submemplex. Okay, so this is the basically the notation of the variables. Dmin and dmax is the minimum and maximum allowable values of the limit leaping step size respectively. Xi is the ith decision variable of the new solution, and x new is the new solution. So that is the basically new solution you are calculating. Now I will, after covering this whole algorithm, I will give you this code, the MATLAB code for the shuffle frog leaping algorithm. Okay, I will give you. Now you need to apply in your problem. Okay, so I will give you some problems, and there you are going to modify that algorithm and you have to show. So you have to submit those things with in the form of assignment. Okay, so I will give you the entire code of the shuffle frog leaping algorithm. Okay, so that you can also in your, let us say, electrical problem, or let us say in your electronics engineering problem, you can also apply. Okay. So otherwise, X new is generated based on the P base instead of M based. So if, let us say, what we are going to see, if X new is better than M worst, sometimes what will happen, see, whatever we have done, we are in the last step, we have seen that this M worst is updated. It is a updation of the M worst. So the worst frog within that particular colony, it has been given the chance to improve. Now, if it is found that really that worst frog has improved its performance, then what we'll do? We'll basically replace that particular frog M worst by the new one. That means that time this M worst will be deleted and X new will take the position. Okay. Otherwise, so if we are not getting, let us say we are with X new, it is not better than this M worst. What will happen? We have to do X new is generated based on the P base instead of M base. So there are two kinds of strategy. One is from the colony, the best one is selected, and from that the distance is calculated, and then the position is updated. Okay, but if it is found that within the colony that particular worst frog has no chance to improve, so then what has to be done? We will take help of the best one, global best one. Within the entire population, entire colony, all the sub-memeplexes, memeplexes, there will be a best one. So that best is selected. And from that best frog, the particular individual frog will calculate the distance. So XP best I minus XM worst I, this distance is calculated and it is updated with the XM worst. Worst will update. So this is the new one. Xi dash is the new one. So previously we have taken here XM best because we have calculated from the colony best. But here, if we are not getting any better performance, then we'll take this step, that is, we'll basically take the distance from the global best. So this way we'll again update the basically the new variable. We'll generate the new variable. So in which XP best is the ith decision variable of the best solution in the entire population. In case X new is not better than the M worst, a randomly generated possible solution substitute M worst. See, first step we'll see that within the colony, which one is the best. We'll update the distance from the XM best. Now we are finding that this solution is not good. Then we'll take the distance from the XP best. Again, we are finding this solution is not good. So the third option, this is the third option. Third option is, in case X new is not better than the M worst, a randomly generated possible solution substitute M worst. So what we'll do, we'll take Xi dash will be basically a new random variables will generate. And those random variables will substitute the M worst value. So the frogs of the Memeplex are ranked according to their fitness value following the replacement of the M worst. So now what we'll do? See, this new thing you have actually this X new is generated either by three ways. I will write here. So generation of this X new generation of this X new. So X new, how we are going to generate? The first possible way is number one, updating worst frog from the meme shared by M best. That means the colony based. Second, if you are not getting, then you have to take the step to updating worst frog from the meme shared by G based or P based here. P based. That means from the best frog among entire colony. Now, after that also you are not getting any improvement. So there is a third step, updating worst frog by replacing it by a randomly generated new frog. Is it clear? Any doubt from this? How we are going to update it? Any question from anyone? Any question? Hello?
No, sir.
Is it clear? Hello?
Yes, sir.
Whether you will be able to apply, आप apply कर सकते हो this algorithm in your problem. Confidence आया इसके ऊपर जो yes I can apply this algorithm. कुछ सीखने के बाद कुछ apply तो करना है ना. Unless and until you apply, this knowledge will be a bookish knowledge. You will not be able to apply it. Unless and until you apply, then this concept will be useless. Okay. So what you will do, when I will supply you this code, the MATLAB code, the entire program, where you can actually these codes are written. So what you will do, you will apply your any problem you will take from this in your discipline or any mathematical function you are going to take and you will apply. Okay, then your basically understanding and this knowledge will be completed. Is it clear? ठीक है, कर सकते हो ना? Huh?
Yes.
Okay, because that has to be done, because otherwise learning this artificial intelligence, subcomputing, so this will be only you have to apply it, because theory you can learn. When you will apply it, then really you can basically understand the beauty of these particular applications. Okay. So, okay, so I will stop here. We'll continue in the next class. Thank you. So I will take first the attendance. Just a minute. We are having internal test from Saturday. Okay. Yes or no? Your internal test, it is scheduled from Saturday, this Saturday?
Yes, sir.
Okay. So, syllabus from my portion, particle sum optimization, and the shuffle frog leaping algorithm. These two algorithms. Syllabus from my portion. Okay. Okay. Thank you. I will close this meeting.